In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 3, Yield Criteria, Part 9. In this part, I'm going to continue to talk about yield criteria, especially the Moore-Coulomb model for ductile materials. And I'm going to solve an example and to see how we apply this model to a real problem. Okay, as you can see here, this is a machine, and there's a shaft connected to this machine, and this shaft has a pulley on it. The pulley is on the shaft, and there is this belt on this pulley which is connected to another pulley which is connected to the motor and drives the small pulley and drives the larger pulley and drives the machine. Now here we are just considering the forces applied to this pulley. As you know, when we have a pulley and a belt system for transmission, for power transmission, we have to apply pretension on the belt so that the power is transmitted. Now this is the pretension which is applied to the belt as well as the forces due to power transmission. So that's why we have this 450 Newton and 90 Newton in here. Okay, and we are given some dimensions here, for instance the length of the shaft, the diameter of the shaft, the diameter of the pulley, and we have been told that the shaft is made of ductile cast iron grade 60-40-18, right? And ductile cast iron, of course, is a ductile, relatively ductile materials, and the problem asks us to find out the factor of safety against yielding the shaft using the ductile Coulomb-Moore. DCM is ductile Coulomb-Moore criteria, which we talked about it in the previous part. Okay, so we are going to do that. In order to do that, I remind you that this was the Moore-Coulomb model for ductile material, and as you can see, for this kind of materials we have different values for yield strength, in tension and compression, and this was the equation that we obtained before. Now then, let's have a look at our problem here and see what we could do. First of all, we have to find out the stresses applied here. The stress is a flexural stress and is equal to mc over I, and m is the moment applied to this shaft, which is 540, because we have 450 here and 90 here, so we get 540 Newton times 150, which is distance. Okay, this distance is 15 centimeter. Okay, and then times 10 millimeter, which is the diameter of the shaft is 20 millimeter, and that 10 millimeter is C, which is equal to R. So this 450 and 90 are applied downwards, so if we add them together we get 540, and then times this distance, which is 15 centimeter or 150 millimeter, so we get the bending moment on the shaft, and then divided by I, because that's R here, because the cross section of the shaft is circular, so this C is equal to R, and I also for the circular cross section is P over 64, D to the power of 4, D here is 20 millimeter, so we get 103.13 megapascal for the stress applied at the cross section of the shaft. That's the flexural stress. Now torsional stress also, we have some torsion because the stresses, the forces are applied here. So T times C over J. Now T is the torsional torque. In fact, torque is equal to 36,000 Newton millimeter, because that's 450 times 100 millimeter, and that's 90 Newton times 100 millimeter. So that's minus that becomes 36,000 Newton millimeter, and that's the torque. That is C, also is circular cross section, the shaft, and C is equal to R is 10 millimeter, and that's pi over 32, D to the power of 4 for the circular cross section, that's J, and that's I. So we get 22.92 megapascal is the torsional stress applied at the cross section of the shaft. Now from the Mohr circle, we have these sigma A and sigma B. These are the principal stresses, and these are the stresses applied to the shaft, which we obtained here, and we substitute into this equation, and so we get this, because we have here only sigma x and tau. Okay, so that's why we get sigma x here, sigma y is 0, and that's plus minus. Again here sigma y is 0, and tau also we obtained here. Therefore we obtain sigma A and sigma B. Sigma A is equal to 107.99 megapascal, and sigma B is minus 4.86 megapascal. The plus is A, minus is B, and so we can these are the principal stresses, and this was the equation we obtained for the Mohr Coulomb model for ductile materials, and these are the values for sigma A and sigma B. So we plot these values on the axis here, and also note that this was the this is the values for that grade of ductile iron which I was talking about. Okay, the yielding tension is 329 megapascal, and yielding compression is 359 megapascal. Usually these two are equal, but for this kind of material they are different. So if we plot them here, we put them in this equation. Okay, we put these values in this equation, and we get N 2.926. That is the factor of safety which we were looking for. Okay, so if I plot these values, 329 is the yield in tension, and 359 is yielding compression. So I can draw the Mohr Coulomb model in here. That's the yield criteria, and I can put these values sigma A and sigma B, sigma A and sigma B, and see what I get here. That's my point. That's the point, sigma A and sigma B. That's a small point there, because sigma A is 107.99, considering that's 329, so it's somewhere here, and that's minus 4.86, considering that's 359. It will be very near to this axis, so that is my applied stresses. And if I draw a line from here, that will be the load line. If you look at here, you can see that if I increase the stresses, reach this point, the material yields. But for the time being, the state of stress is this. So this part divided by that part is in fact the factor of safety. Okay, so that's how we get the factor of safety. And I have magnified it here to explain it a bit more clearer. That's the load point, that's the load line. Okay, therefore on the load line, if you look at the load point, the length, this length, the total length up to the yield low key, this length divided by this length gives the factor of safety. So you can see we have a fairly good factor of safety. If the load increases, this point moves on the line towards the yield point, and if we decrease the load, it moves that way. Okay, so that's how we apply these more Coulomb model for ductile material in a real example problem. Now then, I want to move on to brittle materials. Okay, this is ductile material, more Coulomb model for ductile material. Now I want to move to brittle material, which have less ductility, and they break at a higher strength but at lower strain. This is the normal behavior of a ductile material, and this is the normal behavior of a brittle material. This blue one is a brittle, the red one is ductile. Okay, so as you can see, the difference between this equation and the previous equation is what? Here you see on the denominators we have SYT, SYC. That means yield strength. Okay, but here instead of yield strength we have the tensile strength. So the only difference in the equation is that we substitute for the yield, we substitute SUT and SUC for brittle materials, because brittle materials don't have any plasticity. They, in fact, their yield point and the ultimate tensile strength is almost the same. Here I have exaggerated a bit, but that means that we don't have any yield points here. So more Coulomb model for brittle material is like that. Okay, instead of SYC and SYT, we put SUC and UT. U stands for ultimate tensile strength, that point. Now, let's examine this a bit further. So that's more Coulomb model for brittle material, but if we change this a bit, for instance, if we continue this line to here, that value also SUT, and move this to here, we get the modified more Coulomb model. Abbreviation, it is called MM. So that's MM, and that is the DMC. Okay, ductile more Coulomb, and that is modified more Coulomb. Okay, that's how we show it in brief. Now then, so as you can see, this more Coulomb model is a bit conservative relative to the modified more Coulomb. Let's examine this a bit further. Obviously, this is the torsion line or the pure shear, and so that is the modified more Coulomb model. And we have another model, which is, as you can see, this square is also another yield criteria, which is called maximum normal stress model. Okay, so it covers an area greater than both of the previous models. And here we are examining all these models together. And as you can see, we have plotted some points. These are the experimental points for brittle materials. Okay, these are the experimental points for brittle materials. That's the torsion line, and these are the values of SUT and SUC. Now, this is for gray cast ion. The data is for gray cast ion. We have here normal criteria, maximum normal stress criteria, and this is modified Moore criteria, and this is Coulomb-Moore criteria, or DCM. We call this DCM, we call this MM, and that's the normal stress criteria. As you can see, these values in the positive quadrant are good for the normal criteria, also for Moore criteria, modified Moore criteria, or Coulomb-Moore, all coincide together. Okay, here we have no problem. But in here, the data in here, as you can see, these are the experimental data. The maximum normal doesn't give any good results because the maximum normal doesn't cover these. These are in fact inside the yield criteria. It means that according to this yield criteria, the material doesn't yield, while the gray cast ion yields here. So this criteria is no good. In fact, maximum normal criteria is not used anymore. Okay, I have just mentioned it here to complete the discussion. Otherwise, we don't use maximum normal criteria anymore. Okay, now then, the Coulomb-Moore criteria, this one. It's a bit conservative. As you can see, these points, the yield points, they are a bit far away from this line. Okay, this is the yield line, while the experimental shows that this is the yield line. But the modified Moore, as you can see, these are the experimental points, is much more precise, and so it gives a more realistic values, while the Coulomb-Moore gives the conservative values. Okay, so like the Tresca and Mises, we can use different criteria here. If you want to be very conservative, we use this one. If we want to be more realistic, we use this one. For this one, we can use a lower factor of safety, and for this one, we can use higher values of factor of safety. Now, this is the torsion line, okay, as I mentioned before. And if I draw a line like that, that is a load line. Of course, load line could be anywhere, but I've just drawn an arbitrary line here. So it means that the yielding according to the modified Moore-Coulomb model is here, according to the Moore-Coulomb model is here. So if, for instance, I have a load point here, then the factor of safety, that line over that line. Okay, and for the modified Moore, of course, the factor of safety is that distance divided by that distance, which gives a higher factor of safety. This gives a lower factor of safety, as I mentioned before.